So what we're going to do here is investigate whether this is a group. In other words, whether this set of direct proportions is a group under multiplication. So we'll have the same four properties that we need to check, and we need all of those properties to work for this to be a group. So first off, for closure, we need AX times BX to be some other direct proportion CX. For associativity, we need AX times BX times CX to be the same whether we multiply the first two together first or the last two. For an identity element, we need there to be some identity proportion, might be different from the one for addition, so that that identity proportion times any direct proportion is that same direct proportion. And we need to be able to come up with inverses, so that AX times its inverse ZX is that same identity proportion again. So let's try this out. So what we're trying out first is the idea of closure, that if we take two direct proportions, AX and BX, we want to be able to multiply them and get a third direct proportion back. So let's suppose for a second that A is 2 and B is 3, and we multiply 2x times 3x. Well, according to everything we already know about algebra, that's going to be 6x squared. Now that's a problem. The reason for that is now we've got an x squared as our proportion, so we've got like a quadratic proportion instead of a direct proportion. Now remember, direct proportions are things like 2x and 3x that go right through the origin in a straight line. 6x squared is going to be a quite steep parabola. It's not going to be that direct proportion shape at all. So here's a problem. We found a counterexample. So we have this collision effect. This property is not true. And as a result of that, we don't even need to go any further and check the other properties. We know that this is not true. We found that contradiction. And so we know for a fact that this is not a group. So we've still answered that question. We have proof that it's not a group from one counterexample. Now you might be asking, why was one example enough to disprove it, not enough to prove it? The reason for that is when we say a thing, we want it to be true all the time. So if we find even one exception, we know that that thing isn't true all the time. Now, in the case where we're trying to say that it's always true, we can try examples out to help us see how we might go about our calculations, but it's the formulas that matter. Now, we're definitely not going to be able to make the formulas work either, because as we can see from here, we would multiply together the two numbers. So we would have A times B. So the temptation is to say, well, let's let C equals A times B, but that's not how we are multiplying these proportions together here. So we've got a completely different style of formula. Now, the other thing that you might try to do is say, okay, let's say that we write that as ABXX and say that we're multiplying A times B times X. But X is our variable, so that doesn't work either. I saw where some of you were going with that, but that relies on X having a particular value, which would contradict the whole idea of how a direct proportion works. So we found something that is a group, but we found out that this is not a group. We don't even need to do the work of checking the rest of the properties. If you violate one property, you're not a group.